Hello all. Uh, I'm Gitanjali Jana. I'm a PhD student from IIT Delhi. So, I welcome you to this live section of quantum mechanics course. So, in this live section, I will solve some of the problems, which will cover the basic as well as some of the advanced concept related to the problems which were taught in this week. So let's see what we've study in this week. So in week 9, we study about one of the most important experiment, which is Stern-Gerlach experiment. So this experiment, it experimentally confirms the existence of spin quantum number of a particle. So and similar to the other angular momentum like orbital angular momentum, the spin can also be represented by a vector which is Sx, Xy or Sz. So it can have three components like the orbital angular momentum, which we have seen as L, right? So, and similar to the commutation relation that we have seen in the orbital angular momentum case, for spin, we also see a similar kind of commutation relation. So, if we have the x component of spin quantum number and we have y component of spin quantum number, then the commutation relation can be uh, of Sx and Sy can be given by IH cot Sz. So this like the orbital angular momentum where Lx and Ly are incompatible operators. So in spin case also, this x component of the spin and the y component of the spin, they are incompatible. So if we measure one, then we cannot simultaneously measure the other component of the spin. So, this commutation relation, they follow, say, cyclic commutation relation. Like if we have, let's say we have X, Y, and Z, and we want to calculate the commutation relation of Sx and Sy, then it will be given by IH cot Sz. If we want to calculate the commutation relation of Sy and Sz, then it will be given by IH cot Sx. And if you want to calculate the spin commutation relation of Z and X component of spin quantum number, then it will be given by IH cot Sy. And it follows the cyclic direction. So if in the other case, like if we want to go from Y to X, then it will be simply minus IH cot Sz. So what I mean to say is if Sx, Sy is IH cot Sz, then Sy, Sx is simply minus IH cot Sz. So, and we know we have studied that the in case of orbital angular momentum case, the L square and Lz operator, they commute with each other. So we can have a simultaneous eigengate for L square as well as Lz. So similarly here also we have S square and Sz. So and they commute with each other. So the commutation relation of S square with Sz will be 0. And we represent the simultaneous eigengate of this S square and Sz is S ms, where S is the it's a quantum number related to the operator S square, and ms is the quantum number that is related to Sz. So we represent the eigengate by a joint eigengate of this quantum number. Now, if you want to find out the what is the quantum number related to S square, then it will be simply that s into s plus 1 h cot square, and we have seen in the orbital angular momentum case also. In orbital angular momentum case, it was s square eigenvalue is L into L plus 1 h cot square. So similarly here we have s into s plus 1 h cot square. So similarly for Sz, the quantum number is mh cot. So ms h cot. So here the value of m can take minus s to plus s in steps of 1. Okay. So and similar to the raising and lowering operator, which we have seen in previous section, that these are used to raise the quantum state of the system to go from one state to other state. So here also we have raising and a lowering operator, that is s plus and s minus, and the action of this operator on a quantum state SMS can be given by this equation, and this equation is similar to the equation that we have seen in the orbital angular momentum case. So you don't have to remember all these things. If you know the equation for one case, orbital angular momentum case, then you can similarly write down what will be the expression for the spin in case of spin quantum number. Okay, so and S plus is simply the raising operator, and it is given by Sx plus Isy, and S minus is the lowering operator, which is given by Sx minus Isy. So these are all the basic things that is related to spin quantum number. So now let us start this section. So first I will solve some of the basic question, and slowly I will move towards the some of the complicated problems. So let's see our first problem. So the first problem is it's easy to solve. So it is about the spin half particle and its eigenvalue. So let me read out the question for you. So the question is, consider a particle with spin half. Then what are the eigenvalues and eigenvectors of Sx, Sy, and Sz? So so you have a spin half particle. So you have a spin half particle. Now it is asking about what will be the eigenvalues and eigenvector of the spin half particle in x direction, in y direction, and in z direction. So it's important to remember what is the eigenvalue and eigenvector of this three components, so that it will help you to solve the complicated problem. Okay, so let us see what is the eigenvalues and eigenvectors. So this is a simple problem, so I will solve it quickly. So you know that spin SI, it is related to the Pauli matrix, like h squared by 2 sigma I. Sigma is the Pauli matrix. So sigma, where sigma x, you know, it is 0, 1, 1, 0. Sigma y is 0 minus I is 0, and sigma z is 1, 0, 0 minus 1. These are the three Pauli matrix. So if you want to calculate what is xx, then it will be h squared by 2 sigma x. So it is nothing but h squared by 2 0, 1, 1, 0. Right? So now, and sy, let us see what is the matrix for the three component of spin quantum number. So this will be h squared by 2, 0 minus I and I 0. And sz is, so let me write it in the next page. So sz is h squared by 2 sigma z, which is nothing but h squared by 2, 1, 0, 0 minus 1. So if you look at sz is a diagonal matrix, right? So the eigenvalue and eigenvectors of diagonal matrix are easy to find. So if you want to find out the eigenvalue of this matrix, these are nothing but the this will be equal to the what is present in the diagonal elements. So the eigenvalues of this SZ will be equal to the diagonal elements. So you no need to find out what is you don't need to solve this equation that you have used before, a minus lambda equal to 0. If it is diagonal, if you're saying it is diagonal, then you simply have to see what are the diagonal elements. So diagonal elements are 1 and minus 1, and there is h squared by 2 here. So it will be h squared by 2 and minus h squared by 2. Right? So these are the eigenvalues for SZ matrix. Okay, and the eigenvector, you can take it as 1, 0, and this one can take it as 0, 1. Okay, so if it is diagonal, so for any kind of diagonal matrix, you can take these two vectors as a eigengate. One is for the upper element, this one, and the other is for this one. Okay, so let us represent this one as up z, and this one is minus half z. Okay, so now let us see what will be the eigenvalue and eigenvector for Sx. So Sx is h squared by 2, 0, 1, 1, 0, right? So for this, what we have to do, this is a non-diagonal matrix, so we have to solve the equation determinant of Sx minus lambda equal to 0. But because it is a simple matrix, 2 cross 2 matrix, you can easily find out what is the determinant of this one. So this will be nothing but minus lambda h squared by 2, h squared by 2 minus lambda equal to 0, right? So this will be equal to determinant of, sorry, the determinant will be lambda square minus h squared by 2 square equal to 0. So that means lambda is nothing but plus or minus h squared by 2. So the eigenvalues of Sx is also plus or minus h squared by 2. So now let us see what is the eigenvector. Or let's say lambda 1 equal to h squared by 2 for the first value. So for this, what you have to do, you have to solve Xx. Let's say eigenkate is AB equal to lambda times lambda 1 times AB, right? So this will be, this is nothing but 0, 1, 1, 0, and there is a h squared by 2 here, AB equal to h squared by 2 AB. So that means if you solve this matrix equation, you will see B equal to A. right? If you solve this one, you will see b equal to a. And for the second case also, like this one, you will see same b equal to a. So that means the eigengate, let's represent it by half x equal to ab, which is nothing but a. So if you want to normalize it, then it is nothing but 1 by norm of this matrix. Norm of this matrix is nothing but square root of 2 into a. So that means the eigenvector is 1 by root 2, 1, 1. Right? So this is one of the eigenvector that is related to the eigenvalue plus h cut by 2, which is 1 by root 2, 1, 1. Now if you see at this eigengate, you can write it as 1, 0 plus 0, 1, right? So this is nothing but the eigenvector of Sz with eigenvalue plus h cut by 2. And this is eigenvector of Sz with eigenvalue minus half minus h cut by 2. So that means you can represent the eigengate of the Sx, which have eigenvalue plus h cut by 2 as linear combination of the eigengate of Sz operator. Okay. So this is how you can write one in terms of other. Now, if you want to see what is the eigengate related to the eigenvalue minus h cut by 2. So you have to solve the same eigenvector equation. Let's say the eigengate is CD, which gives lambda 2 times CD. So this is h cut by 2, 0, 1, 1, 0, CD equal to minus h cut by 2, CD. So this will cancel. Now, if you solve this matrix equation, you will, previous case, you see that A equal to B. Now, there is a minus term. There is a minus term here. So, for this minus term, you will see D equal to minus of C. Okay. So, now the eigenvector is, let's represent it by minus of, which have eigenvalue minus h cut by 2. And we are looking for x. Then this is nothing but CD. C minus C, and after normalization, you will see it is 1 by root 2, 1, 1, 1 minus 1. Now, this one also you can write it as linear combination of the Sz eigenvector, right? So 1 by root 2, this is 1, 0 plus, there is a minus 1 here, right? So it is, will be minus 0, 1. So that means this is 1 by root 2 half z minus half z. Okay. So these are the eigenvector of the Sx operator. Now, if you want to find out Sy, you have to follow the similar process. Sy, let's see the matrix. It is h cut by 2, 0 minus I, 0. So what you have to do? You have to solve determinant of Sy minus lambda equal to 0. So that means it will be minus lambda minus I h cut by 2, I h cut by 2 minus lambda equal to 0. And this is nothing but lambda square minus h cut by 2 whole square equal to 0. So here also we see that the eigenvalues are plus and minus h cut by 2, right? So eigenvalues of Sy also it is same to Sx and Sy, it is plus or minus h squared by 2. Now if you want to find out the eigenvector, then what you can do is to take Sy and take the eigenvector as AB and take one of the eigenvalue h squared by 2 and solve this equation. So let me quickly write it down. What will be the eigenvector? So this is AB. So this will cancel. Now if you solve it, you will see minus IB equal to A. There is an item, so that's why you will see a minus IB. So now that means the eigenvector which is related to plus h squared by 2 of y equal to minus IB B. So this means if you normalize it, it will be equal to 1 by root 2 minus I1. So this is one of the eigenvector which is related to the eigenvalue h squared by 2. Now if you want to find out minus h squared by 2, I am leaving this for you to calculate. So what you see, it will be equal to 1 by root 2 I1. Okay. So this is what you will get. So let me summarize what we have seen. So for spin, we have Sx operator, Sy, and Sz. The eigen values of these three Sx, Sy, and Sz are equal. You will get plus h squared by 2 and minus h squared by 2. It is for spin of particle. For other spin, it will be different. For spin of particle, it is plus h squared by 2 minus h squared by 2. And Sy will be also eigenvector is plus h squared by 2 minus h squared by 2. And Sz also the spin will be plus h squared by 2 and minus h squared by 2. Now the eigenvector of this one, it is nothing but 1 by root 2, 1, 1. And this one is 1 by root 2, 1 minus 1. And for this, it is 1 by root 2 minus I1. This one is 1 by root 2 I1. And this one is simply 1, 0 and 0, 1. Okay. So please remember this eigenvalues and eigenvector because in exam, you don't have to calculate what is the eigenvalue and eigenvector of this matrix. You can directly use this and solve the problem. It will save your time. Okay. Now let us see our next problem. So let me read out the question for you. So it is telling consider a particle in eigenstate Sx. So what are the possible results and their probability if you measure the z component of the spin? Okay. So it is given the particle is in eigenstate Sx. Now what we are doing, we are measuring, we have a particle. Now we are measuring the z component of the spin. Z component of the spin we are measuring. Now the question asking about, the question is about if you measure the z component of the spin, then what are the values we will get and with what probability? Okay, so you have a particle which is in eigenstate of Xx. Now we measure the Sz operator. Now it is asking about the results you will get and its probability. So the results are nothing but the eigenvalues of the operator that is acting on the particle and the probability you will get after writing the state of the particle. So let's see. So it was given, it is in eigenstate of Sx. So initial state of the particle is one of the eigenstate of Sx. So in first question we have seen the eigenstate of Sx is either 2, it is 1 by root 2, 1, 1, and 1 by root 2, 1 minus 1. Right? Now we are measuring the Sz operator. So when we are measuring the Sz operator, it's better to write the initial state as a eigengate of the operator. Like we have Sx and we are measuring the Sz. So to find out the probability, we have to express this one initial state in terms of the eigengates of the Sz that is acting on it. So eigengates of Sz is nothing but 1, 0 and 0, 1. And in the first question, I have shown you how you can write the eigenstate of Sx in terms of Sz operator. So this one, you can write it as 1 by root 2, 1, 0 plus 0, 1. So which is nothing but 1 by root 2. This is plus of eigengate of Z and this is minus of eigengate of Sz operator. Or the particle may be in this state or it may be in this other state, other eigenstate, which is 1 minus. And this one you can write it as 1 by root 2 plus of Z and minus of Z. Okay. Now the possible results. They are asking about the possible results when you measure the Z component. The possible result will be nothing but eigenvalues of it will be equal to the eigenvalues of the operator that is acting on it. Uh, is my screen is frozen? It seems my screen is frozen. Are you able to see my screen? Why is it not moving? Okay. So screen is gone. Okay, wait for 1 minute. I will reshare my. Okay, let me reshare my screen. One minute. So I have told you we are now measuring the particle was in Sx state. Now we are measuring the Sz operator. So the results will be plus or minus h cut by 2, right? The eigen will be plus or minus h cut by 2, and the probability of now the question is asking about what will be the probability of getting h cut by 2 in this experiment. So probability of getting h cut by 2, if you see the last equation, it is nothing but the inner product of the final state and the initial state square. So it will be, if you see there is a 1 by root 2 term here, so the square will be nothing but 1 by root 2 square, so it will be half. So probability of getting the plus h squared by 2 is nothing but half. Okay, so this is how you can solve the problem. So for minus h squared by 2 also, the probability is also same because there is a 1 by root 2 term here. So the probability will be 1 by root 2 square. So this will be half. So let us see the second question. So please go through the second question. So the second question is about the let us read the second question. So it is about for a spin hub particle placed in a magnetic field B. The Hamiltonian H is given by minus gamma B Sy, which is equal to minus omega Sy, where Sy is the y component of the spin quantum number. Now it is telling the state of the system at time t equal to 0 is psi t 0, which is equal to plus state. So it was given the initial state of the system, which is plus, where, and it is also telling where s state when it acts on plus or minus operator, plus or minus state, then it gives plus or minus h cot by 2 and the same eigengate plus or minus. So this is the eigenvalue equation. If you see s state equal, if you see in the question, it is given s state plus or minus kate equal to plus or minus h cot by 2 in the same state. So this means the plus or minus are the eigengates of S Z, which is eigenvalue h cot by 2 and minus h cot by 2. The plus is corresponding to the eigengate plus h cot by 2 and minus is for minus h cot by 2. Now it is telling at a later time t, if S Z measured, then what is the probability to get the value minus h cot by 2. Okay. So Hamiltonian is given and the initial state is given. Now it is asking about the probability of getting the eigengate minus h cot by 2 when you measure the SZ operator. So let us see how we can solve this one. So h is given, if you see h equal to minus omega sy, right? So now we know that the eigenvalues of sy are nothing but plus h cot by 2 and minus h cot by 2. Now, if you see the eigenvector, as I've solved in the first question, the eigenvector corresponding to plus h cot by 2 will be 1 by root 2 minus I plus plus minus plus eigengate plus minus eigengate. Now, if you see the minus h cot by 2 eigenvalue, the eigenvector will be minus 1 by root 2 I times plus eigengate plus minus. Okay, so this is similar to what I have solved in the previous question. So eigengates are plus and minus. Now, if you want to calculate the eigenvalue of h, so h is nothing but minus omega times sy. So sy have eigenvector plus h cot by 2 and minus h cot by 2. That means the eigenvalue of h will be plus omega h cot by 2 and minus omega h cot by 2. So you easily find out what is the eigenvalues of the Hamiltonian operator. Now, if you want to find out what is the eigenvector, which is eigenvalue omega h got by 2, then we have to solve the eigenvalue equation, which is if you see the equation, it is we have taken AB as a eigenvector, first eigenvector, which is eigenvalue omega h got by 2. So if you solve this, what you will see? You will see Sy, you will see the last equation, which is marked in the box, rectangular box. So this will give Sy AB equal to minus h got by 2 AB. So this is similar to the eigenvector calculation for Sy with eigenvalue minus h got by 2. So that means if you want to find out the eigenvector for E1 equal to omega h got by 2, so this will be equal to the eigenvector of Sy, which is eigenvalue plus h got by 2. Okay. So that means the eigenvector of Sy with the eigenvalue minus h got by 2 is nothing but 1 by root 2 I times plus state plus minus state. Okay, so now you have calculated what is the eigenvector for the E1 eigenvalue, and let us represent this eigenvector by phi 1. Now if you want to find out the eigenvector for E2, E2 is eigenvalue minus omega h got by 2. Okay, so if it is let me highlight whatever I am saying. So you can see this one, the eigenvector for for E2, it will be eigenvector of Sy with eigenvalue plus h got by 2. So this you have already seen in the first question. So this will be this one, which is 1 by root 2 minus I times plus state and plus minus state. So let us represent it by phi 2. Now let's see what was the question is about. So question is about uh, the probability of getting minus h got by 2 at a later time t when we measure the state operator. Okay, so first we have to find out what will be the state after a time t, and then we will act state on it and we'll find out the probability. So if you see this equation, the initial state is plus state. Now we act the time evolution operator, which is e to power minus ist by h cut, and it will give the final state psi of t. Okay. So so let us first represent the initial state. So in the previous question, I have told you, if you want to find out the probability, first we have to write the initial state instead in terms of the eigenkate of the operator that is acting on it. So the operator that is acting on it is the acid operator. So you have to write the initial state in terms of the eigenkate of the acid operator. Okay, so let us see how we can write it down. So, so let us see. Let me see the question once. It is in Sy with y component minus h squared by 2. Okay, so the you can add a identity operator in the plus state, right? So it will give. So now phi 1, phi 2. In the previous in this equation, you see the eigenvector of the Hamiltonian are phi 1 and phi 2. So phi 1 is this one and phi 2 is this. So now you are writing the eigenkate of the initial state in terms of the eigenkate of the Hamiltonian operator. Okay. So phi 1, phi 2 are the two complete eigenkette of this Hamiltonian operator. So this if you take the outer product of summation of the outer product of this Hamiltonian eigenkette, this will give 1. So that's why I have added phi 1 outer product phi 1 plus phi 2 outer product phi 2 acting on a state and plus. So now if just take this state inside and multiply it with the individual terms. So now we will get this one, the equation 1, which is nothing but the inner product of phi 1 with plus state, this first term with phi 1, and the inner product of phi 2 with the initial kate and phi 2. So you have to find out what are these values. These values you can, you know, phi 1 and phi 2, the expression for phi 1 and phi 2 in terms of plus state and minus state. So inner product, the inner product of this phi 1 with plus state and phi 2 with plus state, you just have to calculate using equation 2 and 3. So phi 1 you already know this one. So if you take the inner product of, now what you have to do, you have to take the bra of this phi 1 and take the inner product of this bra of phi 1 with plus state. So this will give minus I by root 2. Similarly, phi 2 you already know, which is 1 by root 2 minus I times plus state plus minus state. So now what you have to do, you have to take the inner product of phi 2 with plus state. So for that, from that you will get I by root 2, which is equation 3. So now we just have to put 2 and 3 into 1. Okay. So now you got the initial state psi 2 0 equal to minus I by root 2 phi 1 plus I by root 2 phi 2. Now to find out what will be the state after time t, what you have to do, you have to operate the time evolution operator, which is e to power minus I h cot t by h cot, h t by h cot. So you just simply write what is psi of t0, which we have got here. So now what you have to do is to operate this time evolution operator on the individual state phi 2 and phi 1, right? So now if Hamiltonian operator operates on phi 2, which is a phi 2 and phi 1 are the eigengates of Hamiltonian. So if this time evolution operator acts on phi 2, then it will give the eigenvalue e to power minus I eigenvalue which have eigenvector phi 2. And in this one, you see the eigenvector. If you see this one, the eigenvector for phi 2 is minus omega h cot by 2. This one, right? This will be minus omega h cot by 2. So you have to just put minus omega h cot by 2. So this will become plus e to power I omega sy t by h cot. Similarly, for phi 1, when E acts on phi 1, then it will give the eigenvalue, which is omega h cot by 2. So you will get e to power I omega. So there will be minus here. I forgot to write the minus. So there will be minus here, minus I omega syt by h cot. So now you see there is one operator sy here. So sy when it acts on phi 2, it will give h cot by 2. So the h cot will cancel. So the final term will be e to power I omega t by 2. In the second case, you will get e to power minus I omega t by 2. Right? Now you already expressed the final state in terms of phi 2 and phi 1. Now let's see what will be the probability if probability of getting minus h cot by 2 when we measure the state operator. So the probability is nothing but given by this equation. So plus minus h squared by 2 corresponding to the minus state. So what I have done, I have taken the inner product of the minus state with the final state psi t, inner product square divided by psi t inner product. So psi t is normalized, so the denominator is 1. So what you are left with is nothing but the inner product of a minus state with psi t mod square. So now use equation 4 to get what will be the inner product. So here I have clearly write down what what is the value of inner product we will get if you take the inner product of minus state with psi t. So if you take, then you will get, there will be inner product of phi 1, phi 2 with minus state, and there will be inner product of minus 1 minus with phi 1 state. So this is nothing but 1 by root 2. If you see equation 2 and 3, use equation 2 and 3, then you will see the inner product of minus 1 minus with phi 2 state will be 1 by root 2. Similarly, the inner product of minus with the phi 1 state will be 1 by root 2. So there is a common factor 1 by root 2. So let's take it out. So 1 by root 2 is here, and there is 1 by root 2 here also and here also. So the total will be I by 2, and you will get a exponential term, which is e to power I omega t by 2, and the other term is e to power minus I omega t by 2. Okay. So this equation, this is nothing but this equation, this is nothing but 2i sine omega t by 2, right? E to power I theta minus e to power minus I theta is 2 times I sine theta by 2. So this will give minus sine omega t by 2. So you will get the inner product of the minus state with psi t, which is sine omega t by 2 minus sine omega t by 2. Now, if you want to find out the probability, it is nothing but the square of this inner product. So you will get sine square omega t by 2. Okay. So the probability you will get is sine square omega t by 2, which is answer D. Okay. If you see answer D, so the answer will be D, which is sine square omega t by 2. I think this problem is clear to you. If you have any doubt in any one of the state, then you can ask me. Okay. If you have any doubt, then you can ask me anytime. Just write it in the chat box or just raise your hand if you have any doubt. So if not, let's move to our next question. Let us move to our next question. So please go through the question once before I solve this question. Please go through the question. So let me read out the question for you. So the question is like this. A one-dimensional harmonic oscillator of mass m and frequency omega is in a state psi. So it is given the one-dimensional harmonic oscillator which is in a state psi, and such that the only possible outcomes of the energy measurement are E0, E1 or E2. So this harmonic oscillator is in a state psi, and if you measure the energy, then you will get only E0, E1 and E2, where En is the energy of the nth. Let 1 minute. So En is the, my screen is, okay. En is the energy of the nth excited state. If H is the Hamiltonian of the oscillator, then it is the given this condition, that is, if you take the expectation of Hamiltonian operator, then it will be 3 by 2 h got omega. And if you take the expectation of h square, then it will be 11 by 4 omega h got square. Then it is asking about the probability that the energy measurement will be E0. So, so let us see how you can solve this problem. So it is given psi, when you measure the energy, then the only values you got is either E0, E1 or E2. So that means you can write psi as a linear superposition of this state that have energy E0, E1 and E2, right? So let's say the state for E0 is phi 0, which is this one, and the state for E1 is phi 1, and the state for E2 is phi 2. So now you can write the state as a linear superposition of this phi 0, phi 1 and phi 2 state. Here ABC are the coefficient of phi 0, B is for phi 1, C is for phi 2. So psi is normalized. So we have taken psi as a normalized. So that means A square plus B square plus C square equal to 1. This is the normalization condition. Now let's see what are the expression that is given to us. So it is given the expectation of the Hamiltonian is 3 by 2 h got omega. So that means if you calculate the expectation of this, if you take psi as a if you take this equation 1, then if you calculate the expectation, what you will get is a square time E0 plus B square time E1 plus C square time E2, which is given by this equation. This is what you got if you calculate the expectation. And the right hand side is 3 by 2 h got omega. So now what you have to do, you just have to put the values for E0, E1 and E2. E0 is h got omega by 2, E1 is 3 by 2 h got omega, and E2 is 5 by 2 h got omega. Now if you simplify this equation, you will get equation 1, which is a square plus 3b square plus 5c square equal to 3. So this is the final equation you will get. Now the second condition that is given to us is expectation of h square, which is equal to 11 by 4 omega h got square. Now if you simplify this equation, this expression, what you will get is nothing but this one. You will get a square time e0 square, b square time e1 square plus c square time e2 square. This will be equal to 11 by 4 omega h got square. So similar to the first condition, we have to just put E0, E1 and E2 and simplify the equation. So if you simplify, you will get equation 2, which is A square plus 9B square plus C square equal to 1. Okay. C square equal to 25, C square equal to 11. And the third condition that is given to us is a square plus b square plus c square equal to 1. This is the normalization condition that is given to us. So if we simplify, if we solve equation 1 and 2 and 3, then what we will get is c square is 1 by 4. We will get this. We will get c square equal to 1 by 4. Then b square equal to 1 by 2 and a square equal to 1 by 4. Right? So now you want to find out the probability. So the probability of getting, let's see the question. The question is about the probability that the energy measurement will yield E0. So what is the probability of getting the E0 means the probability of getting the state that is corresponding to E0, which is phi 0. So the probability according to the postulates of quantum mechanics, how can you calculate the probability? It is given by inner product of phi 0 with psi square divided by psi psi. So psi psi is normalized. The denominator is 1. So what you will get is inner product of phi 0 with psi square. So phi 0 with psi square, if you look at the superposition, then phi 0 with psi is nothing but A, right? Inner product of phi 0 with psi is A. So that means the probability is A square, and if you have already calculated what is the value of A square, it is nothing but 1 by 4. So the values you will get is 1 by 4. Okay. So this is how you can calculate the probability state. So the answer is B, 1 by 4. So let us move to the next problem. Let's go through the question once. This question is about the Pauli matrix. And it's a simple question which you can solve easily. So let me read out the question for you. Uh, so the question is, define sigma x as a summation of two operator f and f dagger, and sigma y is a like this, like minus I f dagger minus f, where sigma are the Pauli spin matrices and f dagger obey the anti-commutation relation, which is given by f anti-commutation with f is 0 and f anti-commutation relation with f dagger is 1. Then it is asking about what will be the representation of sigma z in terms of f and f dagger. So sigma x is given to you and sigma z is also given to you. Now they are asking about what is the value of sigma z. So you know that sigma x, sigma z is nothing but if you solve sigma, if you take the product of sigma x and sigma y, what you will get is I times sigma z. So if you want to find out what is sigma z, it is nothing but sigma x, sigma y by I. So now what you have to do, you have to just put the expression that is given to us and solve this. Okay. If you solve this, you will see it will be this one. This is f dagger square minus f dagger f plus f dagger minus f square. So what to simplify this equation to, what we have to do is to use the condition that is given to us. So the condition that is given to us is anti-commutation relation of f with f is 0 and f with f dagger is 1. So if you see f with f is 0, that means f square is 0 and f dagger square is also 0. So which is this equation 3. Now if you see equation 4, then you will see f dagger plus f dagger f is 1. So what you have to do is use equation 3 and 4 and put it in the equation 2. So if you put it, then you will see it is nothing but 2 f dagger f minus 1. Okay. This question is simple. You can easily solve it. But what you have to do, you just have to remember what is the how you can get sigma z when sigma x and sigma y is given to you. Okay, sigma x into sigma y is I times sigma z. Similarly, if you take sigma y with product with sigma z, you will get I times sigma x. And if you take sigma z multiplied by sigma x, you will get I times sigma y. So in this way, you can calculate the other Pauli matrix if two R's are given to you. So the answer will be B. It will be 2 f dagger f minus 1. So are the questions that I've solved till now, are they uh, is everything clear to you? Okay. Equation 3 is how equation 3 is coming. F square is 0 is okay, but how f dagger square is 0. Okay. So if it is given the commutation relation, the anti-commutation relation of f with f is 0. Now if you take the, let me show you in the screen. So this is given to you. This one is given to you. Now if you take the dagger of this condition, the right hand side is 0. So you can take the dagger of this condition. So let me write out. So it is if so let me show you only. So this condition is given now. F with f is 0. So what I have done is I have taken the dagger of this, the whole dagger of this condition. So the right hand side is 0, so it will not be get affected if I take the dagger. So now if you take the dagger of this left hand side, so the equation, the inner the f will become f dagger, right? So from that you can get f dagger square equal to 0. So, is this clear to you or I have to explain again? Okay, yes, fine. So this is how you can get the value for sigma z. So let us move to the next question. Please go through the question once. Question. So let us start solving the sixth question. Okay. So let me read out the question for you. So it is given. Two spin-off particles are described by Hamiltonian H equal to A S1z plus S2z plus B S1 dot S2. Now A, B are these are the constants and S1, S2 are the spin angular momentum of the spin of the particle. Okay. If the state of the system is found to be in S equal to 0 state, then what is the energy of the system. So Hamiltonian is given to you, and there are two spin-up particles. So there are two spin-up particles. So that means if the spin quantum number of first particle is S1, second particle is S2, and the Z component is S1Z, this is S2Z. So when we have two spin-up particle, the total spin of this whole system will be vector sum of S1 and S2. This you I think all know. Now here you can see there is a S1 dot S2 term here, right? So what you have to do is take the square of this S. So this is nothing but S1 plus S2 square. So you will get S1 square plus S2 square plus 2 S1 dot S2, right? So that means if you want to find out what is S1 dot S2, it is nothing but S square minus S1 square minus S2 square divided by 2. Okay, so this is one value we get. So now if S equal to S1 plus S2, that means the Z component of S is equal to the Z component of S1 and Z component of S2. So what I have done is I have, so Hamiltonian, so let me tell you why I have calculated this one. So Hamiltonian is given A times S1Z plus S2Z plus B times S1 dot S2. So what I have done is I have represent S1 and S2 in terms of the operator whose eigenvalues are known to us. Like for spin, we know the quantum, the eigenvalue of S square, we know the eigenvalue of SZ, and also we know eigenvalue of S1 square, S2 square. But what we don't know is the eigenvalue of S1 dot S2. So that's why I have expressed S1 dot S2 in terms of the operator whose eigenvalues are given known to us, right? So that means if you take a, so S square and SZ, they commute with each other, right? So that means you can take a simultaneous eigenstate of these two operators. Let's represent it by S and MS. S1 and S2, they commute with each other because they correspond to two different particles. So you have two particles, one have S1, other one is S2. So if you have different particle, then they will commute. Okay, so S1, okay, huh. So now you take a simultaneous eigengate of S square and SZ. So to find out the eigenvalue, what you have to do, you have to act Hamiltonian on it. So if you act Hamiltonian, you will get a energy eigenvalue with the same eigengate SMS. So let us see what is the left hand side. So left hand side is A S1Z plus S2Z plus B S1 S2. This is the Hamiltonian with SMS. Let us solve the left hand side only. So this one, this is nothing but, this is according to this equation, this is SZ, the Z component of total angular momentum. And this one for S1 dot S2, what you have to do? We have to use this equation. So let us solve it. So you will get S ASZ SMS plus B S1 and S2 dot is half S square minus S1 square minus S2 square acting on SMS. So now you just have to put the eigenvalue. So SZ acting on. So let me write here. So SZ when it acts on SMS, it will give MSH cut SMS because MSH cut is the eigenvalue corresponding to SZ. Similarly, when S square acts on SMS, it will give S into S plus 1 H cut square SMS, right? And when S1 square when it acts on SMS, it will give S1 S1 into S1 plus 1 H cut square SMS. And when S2 square when it acts on, it will give S2 plus 1 SMS. So these are the eigenvalues. Now the equation will become this one. It will become A times MSH cut SMS plus B by 2. You can write this one as S into S plus 1 minus S1 into S1 plus 1 minus S2 into S2 plus 1 into SMS. There is a H cut square term here. So now what you have to do is use the values that is given to you. It was given the particles are spin-off particle. So that means S1 is half, S2 is half. And also it was, if you look at the question, it was given the particle is found to be in a state S equal to 0. So that means this S equal to 0. Here S equal to 0. And if S equal to 0, what will be the possible value of MS you will get? MS will be 0 only, right? If S is 0, then the values of MS, how we calculate it? It runs from minus S to plus S in steps of 1. So if S is 0, then MS will be 0 automatically. So that means this one is 0. So the value we will got is B H cut by 2. This is 0. And this one is minus half plus 1 minus half plus 1 SMS. So this is minus 3 by 4 minus 3 by 4. So that means you got BH cut square by 2 minus 3 by 2 SMS. So this is the eigenvalue. This is the energy you will get for S equal to 0 state. So that means the energy of the particle will be minus 3 by 4 B H cut square. Okay. So this is how you can approach this problem. So it was Hamiltonian was given to you, and there are two particles, and already the spin quantum number of resultant system is given to you. So you just have to express the Hamiltonian in terms of the operator, which eigenvalues are known to you. Do you have any other question? So this problem is clear to you, right? Otherwise, let us move to the next question, if it is clear. Okay, so let us quickly solve the next one. So the next problem, it's a similar kind of problem. So it is given for a spin S particle. So spin of the particle is S. For a spin S particle, in the eigenvalues of S square and SZ, the expectation value of uh, Sx square is what? So it is given the eigenkate Sm is the eigenkate of S square and Sz. So it implies if S square acts on SMS, Sm, it will give S into S plus 1, H chord square Sm. And if Sz acts on Sm, it will give MH chord Sm. Now to calculate the expectation of the x component of the square of x component of spin quantum number. So Sx is not a eigenkate of S and M, right? So what you have to do is you just have to use the raising and lowering operator expression. So Sx is given by S plus S minus divided by 2. So that means this is nothing but Sm S plus S minus divided by 2 whole square. So you just have to solve the square of this the Sx. So it will give S plus square plus S minus square, and there will be two terms, S plus S minus plus S minus S plus divided by 4 and Sm. So now let us see the individual terms. So this one you can write it as S plus square plus Sm S minus square, and there is, so 4 is there, and there is a cross term 1 by 4 Sm S plus S minus plus S minus S plus acting on Sm. So now you know that if S plus, if it acts on Sm or S plus square, then it will raises the state of the system. So it will take S to S plus 1. No, sorry. So it will changes the state of the system. So let us see what is the expression for the S plus. So S plus S minus is given by this equation which I have shown you in the first slide. If you see this term, so it changes the uh, magnetic quantum number of the system. It takes a plus operator changes M to M plus 1, and minus or a lowering operator takes M to M minus 1. So that means, let us see what will be the value we'll get. So that means when S plus act on Sm, it will changes square when act on Sm. It will change the state to S to M plus 2, right? So that means this inner product will be 0. You will get some value here with the state this. Now if you take the inner product of this one with Sm, will get 0. Similarly, when S minus square, when it acts on Sm, it will lowers the state of the system. You will get A minus 2. So it means this one is also 0. And the terms that will remain is 1 by 4 Sm S plus S minus S minus S plus Sm. So what you have to You can use how this S minus and S plus act on this SM to calculate this value. And the other way to calculate is to remember that S plus S minus S plus will be equal to 2 times S square minus S z square. Just remember this equation. You can get it by putting S plus is X plus IXY and S minus is Sx minus ISY. If you solve it, you will get 2 times S square minus S z square. And this S square and S z square eigenvalue you know already. So now we can calculate what will be the value. So there is a 2 here. This is S square minus S z square. This side. So the value you will get is half. When S square act on SM, it will give S into S plus 1 h cut square minus when this one acts on this, it will give m square h cut square m square s cut square. So that means the expectation of s square is this one, s into s plus 1 minus m square. This should be the answer you will get. Let us see. Okay, the option 1. So this will be the answer you will get. So let us move to the next question. Okay. It is given if S1 and S2 are the spin operator of two electrons of helium atom, then the value of S1 dot S2 is for the ground state. So this one is easy. So let me quickly solve it. So S1 dot S2, I have in the previous question I have calculated what is the value of S1 dot S2. It is nothing but S square minus S1 square minus S2 square divided by 2. So this one you will get h cut square by 2 s into s plus 1 minus s1 plus 1 minus s2 plus 1. S1 and S2, you know it is half. So that means S1, S1 plus 1 and S2 plus 1 will be 3 by 4. And for S can be, S is nothing but the vector sum of S1 and S2. And this is half and half. So you will get, if you take the vector sum, you will get either 1 or 0. So that means the S1 and S2 dot you will get is h cut by squared by 2. Let us take s equal to 1. So you will get 2 minus 3 by 4, 3 by 4, that will be 3 by 2. So you will get 1 by 4 h cut square. The other one is by taking s equal to 0. H squared by squared 2 and there will be 0, so it is 3 by 2. 3 by 4 h squared. So the lowest expectation you will get is this one. So that means for ground state, it is minus 3 by 4 h cot square. This one. This will be the answer. So I think till now every problems is clear to you. If you have any problem doubt, then ask me. You can ask me anytime. Otherwise, let us move to the next question. It's possible to get s equal to 1. So when both the electrons are in spin up and spin up state, then you will get means plus spin up plus h cut by 2 and plus h cut by 2. Then in that case we will get s equal to 1. If not, replace state, right? It is similar to saying it's a different state. S equal to 1. Let us move to the next problem. So go through the question once. So it's based on the uh, Stern-Gerlach experiment. So let me read out the question for you. So it is a uh, P is a beam of atoms with spin quantum number half and 0. So it is given spin quantum number. So P is a beam of atoms with spin quantum number. Let's write it as S equal to half. And other one is orbital quantum number, which is L equal to 0. All with angular momentum h got by 2 along the x-axis. So it is given these atoms that constitutes the beam P. It is angular momentum plus h got by 2 along the x-axis. Now we have another beam which is Q. So we have another beam Q, and it's similar. That means S equal to half for this case also and L equal to 0. But it is not defined in which direction the spin is oriented. So it is a beam of unpolarized atoms. So this is a unpolarized. Now in question A, let us see the question A. What is the spin state function of P in terms of alpha and beta, where alpha and beta are the eigenfunction of S jet? So it is asking about what is the spin state of the beam P in terms of alpha and beta, where alpha beta are the minute. Eigenstate of S jet. So eigenstate of S jet are nothing but 1 0 and 0 1, right? So let us represent 1 0 as alpha and this one is beta. And it was given the atoms that is present in the beam P, they are oriented along the x direction and eigenvalue plus h cut by 2. So that means the eigenstate will be the eigenstate of Sx, which have eigenvalue plus h cut by 2, right? So that means the spin state of P will be equal to the eigenkate of Sx, which have eigenvalue plus h cut by 2, and this is 1 by root 2. 1, you already know this one. So that means the SP will be equal to 1 by root 2. 1 you can write it as alpha plus beta. So this is nothing but alpha plus beta by root 2. Now, the second question, it is given if the two beams, that is beam P and beam Q, are passed separately through a Stern-Gerlach apparatus with its magnetic field along z-axis, then is there any difference between the emerging beams in the two cases? So now what it is saying, beam P is passed through a Stern-Gerlach apparatus which a B equal to Bz cap, and similarly the beam Q is also passed through the Stern-Gerlach apparatus, same apparatus. Then it is asking about whether the beams you will get, whether you will be able to differentiate between these two beams or not. So if you, it is given, it is the atoms in PR plus h cut by 2 oriented along x cap direction, and this Q is unpolarized. Now if you pass through the atoms of BMP to a apparatus which have magnetic field in the z direction, you know that it will get splitted into two parts. One will have Sz equal to plus h cut by 2 eigenvalue, and the other one will have Sz equal to minus h cut by 2. Because Sx and Sz are incompatible, so you will get two beams. Now, if we pass through a beam Q which have no specific direction, so if you pass through this same Stern-Gerlach apparatus, then you will see the same result, right? Because it will give two eigenvalue. One will give plus h cut by 2 Sz, and the other will give Sz equal to minus h cut by 2. So what you will see in the screen is, for P you will get two spot, and for Q also you will get two spot. One is for h cut by 2, other one is for minus h cut by 2. This one is also for plus h cut by 2, minus h cut by 2. So that means you won't be able to differentiate between between these two beams. So the answer will be no, right? Now it is asking whether experimentally you can differentiate between these beams or not. So if you experiment, if you are doing experiment, then how can you differentiate between these two beams? So for that, what we have to do, we have to look for what is the spin orientation of these atoms. So for P, it was given these are oriented along the x direction, which have eigenvalue plus h cut by 2. And for Q, it is unpolarized. Now, if you pass this beam P to a apparatus which a magnetic field in the escape direction. So, what is the number of beams you will get? You will get one beam only, because it is given already the atoms of P are oriented in plus h cut by 2. So if you pass through the Stern-Gerlach apparatus which have magnetic field in the B direction, it will pass all the atoms in the same state, h cut by 2. You won't get minus h cut by 2 here. But if you pass this unpolarized beam, to the same apparatus which a magnetic field in the escape direction, you will get two beams here because there is no specific orientation of atoms in Q. So you will get Sx equal to minus h squared by 2 and Sx equal to minus h plus h squared by 2. So that means if you have two beams, now you can differentiate it. So for P, if you have a apparatus B equal to Stern-Galler apparatus where magnetic field in the x direction, for P you will get one spot, for Q you will two spot. So this is how you can differentiate between these two beams. Okay. So the next question is about the time reversal operator. So similar to the parity inversion operator, like the parity operator where if you act a parity operator P on a state R, it gives minus R, right? So similar to this, we have time reversal operator. So that the time reversal operator in time reversal operator, what will happen is the t days will become minus t. So the time reverses. T goes to minus t. So if you have initial states, let's say psi xt, then if you act the time reversal operator t, then it will become psi prime x t prime, where t prime equal to minus t. And in this time reversal, how the operator changes? The operator changes if like the unitary transformation. Here we have time reversal transformation of an operator. If you have an operator A, then under time reversal symmetry, it will become A dash, which is equal to T A E minus and other, and let's say how the operator is R, then under time reversal it will become TR T minus. And some of the properties of this time reversal symmetry is this one: if you have position operator, then this transformation is equal to R only. And if you have, let's say, momentum, then this transformation will give minus P. So these are the properties of time reversal symmetry. So these are not required for this question, but this I have mentioned, which you can use in other question also. So let us see what is given in our question. So it is given the Hamiltonian operator is invariant under time reversal. So invariant under time reversal means if you take the let's say we have Hamiltonian H and we have time reversal symmetry. So it will become H prime, right? This one become H prime. Now H prime you can write it as T H T prime, sorry, T minus inverse of the time reversal symmetry. So if it is given the Hamiltonian is invariant under time reversal, so that means H prime is equal to H. So under the time reversal, it is remains unchanged. So that means the TH T prime equal to H. So this means TH equal to, if you multiply the T from right hand side, then you will get TH equal to HT. This what you mean by time reversal invariance. So let us see what is given in our question. So it is given the Hamiltonian operator is invariant under time reversal and psi is an eigenstate of a spinless system with eigenvalue E. Then it is telling whether T psi is also a eigenstate of H with same eigenvalue or not. Okay, so it is given psi is an eigenstate of H with eigenvalue E. Now it is asking whether T psi is also eigenstate of H with same eigenvalue E. So let us check. So it is given S psi equal to E psi. Now if you multiply a T operator, so T psi equal to T E psi, right? Which is nothing but E times E psi. And from this equation, you can see TH equal to ST. So you can write ST psi equal to E times T psi. So this is nothing but a eigenvalue equation with eigenvector T psi. So that means the if you have a Hamiltonian that is invariant under time reversal, and the eigenstate of this Hamiltonian is psi with eigenvalue E, then the the same Hamiltonian will have eigenstate T psi with same eigenvalue E. So that means the answer will be true. The physical meaning is like you uh, reverse the process in which you proceed. Like if you are going from A to B, in time reversal, what you do, you go from B to A. So you reverse, uh, like if you play a video, okay. So if you play a video, you are going forward, right, in time. Now, if you back the video, then this is what we mean by time reversal. So we go back in time to check the state of the system. Now, if the operator is time invariant, then if you go back in time, then you will get the same value. So time reversal is nothing but going back in time. So what happens sometimes some of the states are time reversal invariant and some of the states are time reversal variant. So that means if you go back, if you are going from A to B, then you will get one value. But if you are going from B to A, then you will get another value. But if it is time invariant, then you will get same value in both A to B and B to A. It's like, let me give an example. If you have a, let's examine a optics experiment. If you have a substrate and now if you are putting a light on it, so you are going from this direction to this direction, right? From top to bottom. So in time reversal, what you do, we put the light in bottom part and see whether the response is same or not. Okay. Instead of going this, we go this. I think the time reversal symmetries, I think you have understood it. Otherwise, let us move to the next question. Parity operator is like a coordinate transformation. So you go from R to minus R. It's like mirror, taking a mirror symmetry. You go from R to minus R. By coordinate transformation, if you mean spherical to cylindrical, that is not what I mean. It's just by coordinate transformation, by you mean, okay. It's not like you go from spherical to Cartesian, Cartesian to polar. This is not like that. You take the mirror image of this. Huh. It's like this only. So let me explain the next one. So next one is based on the coherent state of the system. So if alpha represent the coherent state of the system, then what is the expectation value of energy? So coherent state by if alpha is a coherent state, that means you can this coherent state satisfies the condition A alpha equal to alpha times alpha. So if you act a lowering operator on alpha state, then you will get the eigenvalue alpha times alpha. This is what we mean by coherent state. Now it is asking about the expectation value of energy in this coherent state. So expectation value is nothing but alpha times H alpha. So alpha time H we know it is nothing but H cut omega A dagger A plus half times alpha. So that means is H cut omega alpha A dagger A alpha plus half alpha alpha. So this is one. Now if you take it is given A alpha equal to alpha times alpha. That means if you take the dagger, it will become alpha times A dagger equal to alpha star alpha. The bra operator alpha. So what you have to sorry. So what you have to do is you just have to put this expression in this one. So this will give alpha H alpha equal to H cut omega alpha square plus half. This is the energy eigenvalue that you will get in a coherent state. Now, the expectation value of energy that you will get in a coherent state. So this is the answer. So these are based on the coherent state. Okay. So let us move to our next question. So next question is prove that the coherent state alpha can be generated from the vacuum state 0 by the displacement operator. So I am solving these problems because it will be useful. It will be useful to you to simplify some of the other problems. Okay. So you just have to remember these facts. So if let's say if we have a coherent state alpha, then we can generate this coherent state alpha by taking the displacement operator on the vacuum state 0. It's better if you remember this statement. So instead of but for coherent state we know that A alpha equal to alpha times alpha. So let us prove in a reverse way. Like let us check whether by taking this condition we are getting this value, this condition or not. If by taking this one, if we are getting this, then it means that this condition is true. So that means we can generate the coherent state by acting the displacement operator on the vacuum state. So let us prove that way. So let us take alpha equal to d alpha 0 and check whether we are getting the coherent condition or not. Now let us check the left hand side, which is A alpha. So you know that the displacement operator a unitary operator. So that means you can take it as a you can what I mean is d alpha d dagger d dagger alpha is 1. So what you have to do, you have to just put this equation here. So let us check D alpha, D dagger alpha. So remember these facts. These are useful to solve the question quickly. Now, what we can do, we can put the value of alpha by taking this expression. So E times alpha is D alpha acting on the vacuum state. Now this condition, I think you must have remembered this condition. This is there, I think, in week 8, last video of week 8. So this condition is nothing but this will be D dagger A alpha. Let me see. This will be A plus alpha. Okay. So this is the simplified expression for this terms. So that means this is D alpha A times 0 plus alpha times 0. This is A times 0 is 0 because if lowering operator acts on the lowest state, it will give 0. So the terms that will remain is D alpha, alpha times 0. So we can write it as alpha, D alpha 0. And D alpha 0 is nothing but alpha, right? So what we get is we take the left hand side of this covariant equation, we got alpha times alpha. So that means this condition is true. So we can get the covariant state by acting the displacement operator on vacuum state. Okay. So remember this small useful facts like the displacement operator is unitary. You can get the covariant operator from vacuum state. And this condition D dagger A D equal to A plus alpha. So remember this. So before ending this section, let us solve this one. Then we can end our section. This is also based on covariant operator, covariant state. In the last question we can solve in the next section. So it is given alpha is a covariant state, then what is the value of 0 alpha? The inner product of the vacuum state with alpha. Okay. So what you have to do is alpha is given and it's a covariant state. So that means A times alpha equal to alpha times alpha. So if you want to find out D alpha, and in the previous question, we have seen that we can get the covariant state by acting the displacement operator on the vacuum state. So let us use this fact here. So this will be D0, D of alpha times 0. Now one of the expression for the displacement operator is like this. The expression for displacement operator is e to power minus alpha square by 2 e to power alpha dagger e to power alpha star. This is the expression for the displacement operator. So what you have to do, you have to put this expression here. So e to power alpha square by 2, it's a constant, you can take it out. Then what will remain is e to power alpha dagger e to power alpha star a acting on 0. So now what, to simplify this, what you can do is just check the expression for this two exponential. So the first one you can write it as 1 plus e to power, 1 plus alpha a dagger plus alpha a dagger square by 2 factorial. This is the expansion series for the exponential. And the for second term, you can write it as 1 plus alpha star a plus alpha star a square divided by 2 factorial. acting on state 0. Now if you see, there is a dagger here, there is a dagger square here, and there will be a dagger q, and there is also a here, there will be a square here. But when a dagger, when it acts on 0, it will change the state to 1. Now if you take the inner product of 1 with 0, it will be 0. Similarly, if a dagger square acts on 0, it will give 2, and the inner product of 0 with 2 will be 0. That means these terms will give 0 value. Similarly, this term will also give 0 value because they changes the state of the system. So what will remain is 1. So that means this is nothing but alpha square by 2, 0, 0. So it will minus alpha square by 2. So that means if you have a coherent state, so in coherent state, the inner product of the vacuum state with the coherent state is nothing but e to power alpha square by 2. So remember this useful small facts. It will help you to solve the complicated problem. So in if there is a complicated problem like more than this, then you can use the facts like alpha is a uh, alpha, you can get it from the displacement operator and this expression for displacement operator. You can use this fact to solve other problems. Okay, this will help you to solve the problems quickly. So I think all the problems that I have solved today is clear to you. If you have any doubt, you can ask me now. Otherwise, let us end the section. If you have any doubt, then ask. Okay, okay. Okay, okay. Thank you very much for joining this section. So let us meet in the next Saturday. So bye.